Okay, so now we're going to work on a couple of quick tips on graphing transformations of exponential functions. But before we do that, I want to show you a couple of quick patterns that will help you graph any exponential function. So this is, of course, y is equal to 2 to the x, which is a base of 2. Okay, but in general, y is equal to b to the x. How do we find our 3 key points and then go from there? So y is equal to 2 to the x, not too bad. Okay. First of all, 2 to the 0 is 1. 2 to the 1 is 2, 4, 6, 2, 4, keep doubling each time again. A common ratio, so that if we look at differences, it's not going to work because it's multiplicative. Okay, it's growing exponentially. So it means when I go from here, it's times 2, times 2, times 2. That gives you a common ratio. So you see a ratio of 32 over 16, these two, which is equal to 16 over 8, which is equal to 8 over 4, which is equal to 4 over 2, which is equal to b. Of course, in this case, 2. Okay? So that's what you're going to see from these patterns that exist. Okay? And here's the function looked at very carefully and clearly. Okay? So this is -1 again. 2 to the -1. It's not going to be a negative number. 2 to the -1 is 1 over 2 to the 1, or 1/2. Or I'm going to make it 0.5 just so we can easier, but I can put a 1/2 here as well. Okay? 2 to the -2 is 1 over 2 to the 2, which is 1 over 4, which is 0.25, or 1/4. And then 2 to the -3 is 1 over 2 to the 3, which is 1 over 8, which is 0.125, or 1 over 8. And what we're seeing, of course, is we're getting large numbers all the way over here at 5, but when we're going from negative through 0 to positive, we're getting small numbers, we're getting bigger and 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 bigger. So it's an increasing relationship. And we know it's increasing because, of course, the a value is greater than 1. Anything bigger than 1 is going to increase. The bigger the number, the faster it increases by, because you're multiplying each term from 1 to 2 to 3 to 4 for x values by either 2, or if this is a 3, you're multiplying it by 3. If it's a 10, you're multiplying it by 10, and so on. Okay, so the bigger the number, the more dramatic, or what we call exponential, the increase. Okay, so we have it crossing here always at 1, because 2 to the 0 is always 1, and that's an untransformed function. As soon as we translate, that modifier changes. But for every function, if we have a vertical stretch, vertical compression, horizontal stretch, horizontal compression, vertical reflection, horizontal reflection, all of those will still create a scenario where we have a point at 0, 1, or maybe 0, -1. Okay? All right, so where are we? Oh, yeah, so 1 and 2. And 2 and 4, and 3 and 8, and 4 and 16, which we don't have anyway. Okay, but that's okay. There we go, and that's this dramatic, what we even use the word exponential increase. And then, of course, here we've got a 1/2, and then we've got a 1/4, and then we've got an 1/8, and then we've got a 16th, and so on. And so we see this function approach, but never quite get to 0. Okay, so that's an asymptotic relationship there. And so we have that asymptote. It's difficult to draw an asymptote right on the line there, but there's your asymptote at y is equal to 0. Okay, and that's that value that approaches but never quite gets there. Now, for y is equal to 1 over b to the x, we need to have a concerted table of values, because for those of us who want to use mapping to do our transformations for a, k, d, and c, or for those of us who just want to be able to sketch the function very quickly and then do our step-by-step transformations of a, k, d, and c, which is what we're trying to accomplish today, we still need to know a basic table of values. Okay? So one thing to keep in mind is when we have a generic b here, we don't know what b is. Okay, first of all, one point that's going to be key is always 0, 1. Okay? That's the base parent function. Y is equal to 2 to the x, y is equal to 1/2 to the x, y is equal to 1/10 to the x, y is equal to 0.8 to the x, y is equal to 1.2 to the x. Any basic y is equal to b to the x is going to have 0, 1. Then what we're going to do is we're going to have a value here where we substitute in 1. And when you substitute a 1 in there, b to the 1 is just b. So if this is a 2, then it's a 2. If this is a 5, then it's a 5. If this is a 1/2, then it's a 1/2. If this is a 1/10, then it's a 1/10. So 1, your b value. Whatever your b value is, your base. For here, it's going to be the flip of b. So this is literally going to be 1 over b, flipped, because it's to the negative 1. Okay, and remember, we can take a negative exponent by making it 1 over that value, or we can take it as a fraction and we can flip that fraction and make it its reciprocal. Okay, so those are key points. Okay, now, horizontal asymptote is always at, for y is equal to b to the x, or fx is equal to b to the x, is always at y is equal to 0. But once we start doing transformations, you're going to find out that that asymptote, just like it did for the reciprocal function, is going to turn into y is equal to my c value. Okay? Remember, the c value being the value in y is equal to f at, oops, sorry, a f k x minus d plus c. So that c is what I'm talking about. Okay? My domain is always x such that x is a member of real numbers. Always for these guys. Unless, of course, there's some restrictions that are put on in some sort of practical application question. But otherwise, if there's no other restrictions, if it's just a mathematical relationship between x and y and it's exponential, all x values are allowed. Whatever you want. Because we know we can have halves. We know we can have thirds because we've done fractional exponents. Decimals are the same thing as fraction exponents. And of course, quite simply, we can also have negative numbers as well as positive numbers. So we know that all numbers are possible to be able to substitute in there because we've had that many types of exponential relationships. So we know they're all fair game. Range is a bit different of a story. The range is entirely created by our c value. Okay, it's created by this asymptote. Now, for this one, for y is equal to b to the x, it's going to be greater than or equal to 0. But in general, now in general this is the same for the domain. But for the range in general, it's going to be y such that, now it does depend. Y is either going to be greater than or equal to, or less than or equal to, whatever our c value is, and then yer. And we know that because, well, first of all, c is the vertical shift. That's going to shift the asymptote up and down. It's going to shift the function up and down. But what we can have is we can have a negative a value. If we have a negative a value, it's going to make it a reflection in the x-axis. Okay? And as a result, we know that it can decrease as well. So it's either greater than, if my a value, this a value is positive, but if this a value is negative, then it's a less than. Okay? Y-intercepts? Well, the y-intercept, at least to start with, is going to be 0, 1. Okay, but what is it going to turn into? Well, it's going to turn into 0 plus d, just like we do in our mapping rule. Now, 1 over k times 0 is just going to be 0 over k, x over k is just going to turn into 0 over k, which is just 0. But this is going to be 1 times y plus c. So it's just like our mapping rule. That's what it's going to turn into in general. For x-intercepts, okay, it's going to vary. Okay, and x-intercepts are going to entirely be created by the virtue of translating it vertically and horizontally. So if we have an asymptote that, if it's an increasing function, we have an asymptote where y is equal to 0, then we're not going to have an x-intercept. But if we have an increasing function like this, and the asymptote's all the way down here, and it's going to increase like that, then we are going to have one x-intercept. But you should only have one x-intercept. Okay, so 0 or 1. In this case, 0, but it could be 1 or 0 in general. Okay? Describing the curve, the best words to use are increasing. And this is an example of an increasing function, y is equal to 2 to the x, because as you go from negative x to 0 to positive x, okay, it's increasing. So as x increases, y increases. That's why it's called increasing. It's not a linear increase, like a positive slope, but it is a positive increase. It's going to get bigger and bigger and bigger and bigger and bigger. Okay? Where we can also call it a decreasing. In two ways. One, if we have a base that's going to be a half or a third or a tenth or whatever it may be, okay, then it's going to look sort of like this, like that. Sorry, come through the one. There we go. It's going to look like that. But we also have the scenario where we're going to have the possibility of where we take this function, right? Y is equal to 2 to the x, and then we flip it Okay, or we have a horizontal reflection, and that's where our K value is negative. So it can be increasing or decreasing in general. Okay, and you're going to see that pattern play out in some of the transformations that we do. And some of them will be lots of fun, pretty crazy to do. Okay, so that's something to go by as far as how to sketch every exponential function to start with before you start doing your transformations.